we're going to actually get into the bonding. We're going to make the Lewis structures. So there are some rules that you need to follow with respect to making Lewis structures. And if you follow the rules, you'll be fine, because they're just a methodology of following rules. So the first rule is sum the valence electrons from all the atoms. So if you have CO2, that's carbon is 4, so CO2, carbon is 4, oxygen is 6 times 2, that'd be 12, that's 16 electrons. So that's all you're going to do. If you have a cation, you subtract the number. So, for example, we'll do this one later, NH4 plus, that's 5 plus 4 times 1 minus 1, which is 8. If it's anions, you're going to add it. So CO3, 2 minus, that's 4 plus 3 times 6 plus 2, which is 24. So when you're first starting, you just sum the valence electrons. If you do not do this, then you do not know how many electrons you're dealing with. You're going to write the symbols for the atoms involved so as to show which atoms are connected to which. Your first non-hydrogen atom is the central atom, or if it's not clear, and you'll see one of these when I work it, it will be given to you, you will be told. Otherwise, it's the first non-hydrogen atom listed. Now remember, hydrogen can never be a central atom because it can only do one bond and then it's done. A central atom can do way more than that. Okay, then you're going to draw a single bond between each pair of atoms bonded together, and a single bond shares 2 electrons. Then complete the octets of the atoms bonded to the central atom. Resist the urge to multiple bond. You multiple bond when you need to. When do you need to? We'll get to that in 6. You place any leftover electrons on the central atom, even if doing so results in more than an octet. But if there are not enough electrons to give the central atom an octet, try multiple bonds. Generally follow the rules in order. Don't go backwards. And for some reason, some people are just like multiple bond fiends. They like to multiple bond everybody. If you find that you are one of those, resist the urge. And contact me so that I can walk you through how to avoid that pitfall. So now that we have the rules, let's work some problems. So we're going to work a variety of problems. First things first is we have 7 protons. Gosh, it's been a long day already. We have 7 electrons times 2, which is 14, plus 6. So we have 20 electrons involved here. Now, our central atom is going to be chlorine. So we'll set it up with chlorine, and oxygen. Now, I'm going to run out of room over here. That was not smart of me to do that. It's not smart of me to make up elements either. Yeah, that's the other trick. Watch what we have here. We have 2 chlorines and 1 oxygen, not 1 chlorine and 2 oxygen. So we're going to set up the bonds here, single bond, and then we're going to fill the octets of the ones attached to the central atom. So we have 8 around oxygen, we're happy here. We have 8 around chlorine, we're happy here. So that means we have a total of 2, 4, 6, 8, 10, 12, 14, 16 electrons. So then the rule states that if there are any left over, you put them in the central atom. Now notice I'm keeping the north, south, east, west methodology. We look at it, and we're going to call this one carbon 1 and this one carbon 2. If we look at carbon 1, remember the bond counts as 2. We have 8 electrons. Carbon 2 has 8 electrons. Oxygen has 8 electrons. Everybody's happy. We're good. We're done. Now, Notice that I'm actually going to leave space here. When you go to draw these, my recommendation is you leave space because we're going to talk about other things and we'll keep coming back to this structure. And so rather than we redraw them, I'm actually going to come back to different structures that we've already put in. Okay, so I'm going to switch colors to do the next one. So we have H2O2. Well, according to the rules, oxygen should be the central atom with an oxygen and 2 hydrogens off of it. That is not the arrangement, so I go ahead and give it to you. So here we have oxygen, oxygen, and hydrogen. When you have a molecule like this where basically if you put a line through here, it's symmetrical, then if you're asked for shape, you pick either of the 2 central atoms because they're mimics. So let me go ahead and erase that so people don't get confused. We didn't total our electrons, so we'll have 1 plus 6 plus 6 plus 1. So that's 14. So we have 2, 4, 6 already here. 8, 10, 12, 14. Now notice as I'm putting in electrons, I'm putting in pairs. Because with bonding, you're going to get pairs, either bonding pairs or non-bonding pairs. So we have a total of 2, 4, 6, 8, 10, 12, 14 electrons, so we're done. This hydrogen has 2 electrons, so it's happy. This oxygen has 8 electrons, it's happy. This oxygen has 8 electrons, it's happy. This hydrogen has 2, so it's happy. Never, ever, ever give hydrogen more than 2. And don't multiple bond just for sheer entertainment value. All right, so that brings us to the next one, which is ammonia. So we have 5 plus 3 times 1, which is 8. So nitrogen's your central atom. We have hydrogen, hydrogen, and hydrogen. So that's 2, 4, 6 electrons. Any electrons left over go on the central atom. Ta-da, we're good. Okay, that brings us to H2CO. Now, I didn't have to tell you that C was the central atom because it's the first non-hydrogen atom listed. So you should recognize that it is. However, just to keep getting you started, I wanted to help you out here. So that means we have carbon, hydrogen, hydrogen, oxygen. Now, somebody's going to ask, does it matter whether you put the hydrogens first on either side? Can you put the oxygen where the hydrogen is, etc.? And the answer is yes. Well, no. I don't remember what the question was. Does it matter where you position them? No. So we could have done carbon here, oxygen here, hydrogen and hydrogen. Doesn't matter. That doesn't matter. What matters is that you connect them around your central. And you do your math. So this is 1 times 2 plus 4 plus 6. That will be 12 electrons. So we have 2, 4, 6. So we have 6 more to put in. Well, the rule states that you fill the externals first. So 2, 4, 6, 8, 10, 12. Wait. Oxygen's happy. The hydrogens are happy because they're happy with 2. Carbon's short. Well, remember the rule. You can't add extra electrons because if you do, then you end up with an ion. So that's not fair game. So then the rule says that if you need to fill an octet but you can't add any more electrons, then you make multiple bonds. So I'm going to share this one here. So I will rewrite it with the double bond here, hydrogen here, and I left 2 pairs on the oxygen. So there is your Lewis structure. Hydrogens are happy. Carbon has 8. Oxygen has 8. Everybody's happy now in this structure. So when you need to multiple bond, you multiple bond. When you don't, you don't. All right, so here we go again. We have 7. You could read that. 6 times 4 plus 1. Because remember the negative gives us a 1. 6 times 4 is 24 plus 8 is 32. I think that's 32. Sometimes math is kind of optional. So again, the first atom listed is my central atom. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. And again, it doesn't matter which oxygen you start with. It just matters that you keep going around. So this means that if you look at this, chlorine has 8 and each of the oxygens have 8. But this is an ionic compound. So with ions, you put it in a bracket and you put a negative. Because somebody in there has an extra electron. Just not sure who. So later we'll look at who has the extra electron. But right now, when we don't know specifically, and we really don't care, we go ahead and put it in brackets and put the charge on it. So we actually did this one previously, when we're at least the electrons, but we'll do it again. 5 plus 4 times 1 minus 1 is 8. So this one is nitrogen, hydrogen, 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 hydrogen. So if we count the number of electrons that each hydrogen has, it has 2, so it's happy. And the nitrogen has 8, so it's happy. So we're done, right? No. Again, somebody lost an electron, not sure who, so we put a positive on it. And we're good to go. All right, we're going to do one more here. We have 4 plus 5 plus 1. So that would be 10. So we have carbon, nitrogen. Oh, carbon, nitrogen. Okay, first one listed is carbon, so that's the central atom. So we have 2, 4, 6, 8. We fill the outermost of the attached. Anything that's left over goes on the carbon. So now when we look at this, we're like, carbon has 4. Nitrogen has 8. So nitrogen's happy, but carbon's not. So in order to have more, make carbon happy, we need 2 pairs. So we're going to get a pair from here and here. So can you leave it like that? Sure, you can leave it like that if you're asked to draw it. But am I going to give you full credit? No, because that's not a structure. So what we end up with is a triple bond, lone pair here, lone pair here, and because it's a negative, you're going to put it in brackets. So what we did was we went through here and we did electron configurations. Notice in each case, one of the first steps, it may be the first step or it may be my second step, is to ID the number of electrons. If you do not have the correct number of electrons, it is very difficult to get the correct structure because you have to know what the structure is. And up to this point, we have kept the octet rule in place. And you're like, good. Life's good, right? Yeah, life's good, but we have exceptions to the octet rule. There are only 3 exceptions, and the third one's actually the biggest class, but you encounter the first one a lot. These may contain fewer than an octet. Hydrogen has to have 2. Beryllium's kind of psycho. It can have 2, 4, or 6. I don't tend to play with beryllium because it's a little too wonky for me. And boron is happy with 6, as is aluminum. Now, aluminum is in parentheses because for some bizarre reason they always tell you boron, but they don't tell you aluminum. And aluminum you actually encounter more than boron when you do compounds. So those are your ones, and they contain fewer than an octet. Remember, we talked about hydrogen being the duet. So those you just need to know, and as I said, you want to recognize that beryllium's a problem, but I tend to not give you structures with beryllium. Okay. The next one is the one with the fewest exceptions. Oh yeah, that was the point I was going to make before. As we did all of the electron counts before, notice we got even numbers. We got even numbers because that left you with paired electrons. But one of the exceptions is odd number that shouldn't be atoms. Should be an odd number of electrons. And the only one that does this is nitrogen. And I'm about to show you one, and we'll talk about it. But when I give you compounds, you do need to know that nitrogen can disobey the octet rule. But you're not likely to have a structure from me with it. Not to say that it won't appear on an exam that somebody else has created. But bottom line is you do need to know nitrogen can have an odd number. Again, I'll show you structures of these in just a second. The biggest group is the one that can exceed the octet. N is equal to greater than or equal to 3. Well, if we look at that, that means we're going to start with sodium, magnesium, and then we have the empty D block. Then we have aluminum, silicon, phosphorus, sulfur, chlorine, and argon. Now, anything as you go down. Remember when we talked about electron configurations, we said that the S came in the first orbital, then you had, second orbital, second row energy level was S's and P's, and the third was S, P's, and D's, right? But we didn't fill the D's. We waited and filled the D's one below because of energy considerations. So what happens is these are available. They're not in use, but they are available, which means you can pop electrons in them, which means you can exceed the octet. Now, when you exceed the octet, you have 6 pairs max, so 6 regions. But as long as you've got those D's available, so if you look at the periodic table and you go, oh, oxygen could exceed the octet. No, oxygen is in row 2. So in row 2, we only have S's and P's, so the D's are not available. I refer to this as you renting a 2-bedroom apartment, and your parents live 5 hours away. So you're more likely to go see them than they come see you. So you take that second bedroom and you convert it into a study space. Your parents come to visit, brothers come to visit, sisters come to visit, somebody's coming to visit and they need a place to stay. So what you'll do is convert that back to a bedroom. So it is a bedroom. It's just not used as a bedroom most of the time, but you can use it as a bedroom if you need to. So that's what you want to remember is the D's are there. You're just not using them. So let's show you examples of exceeding the octet. Well, phosphorus is 5 plus 7 times 5, which is 35, so we're at 40. So phosphorus is the central, so we have chlorine, 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 chlorine. Notice that I picked off sides, so that's 2, 4, 6, 8, 10 electrons, so we're going to fill the externals. So, where am I? I'm at 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, and 40. So, notice that I've exceeded the octet because phosphorus has 5 regions around it now. And if we look at it, phosphorus is in the 3rd energy level, so we're good to go. Now, the other rule of thumb is just because you can exceed it doesn't mean you have to. More about that later. Sulfur is 6. 4 times 7 is 24. So this is 34 electrons. So sulfur is your central. Fluorine, 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 fluorine. So we have 34 electrons. We have 8 in there. So 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Wait, we have 2 left over. Remember the rule. If you have any leftover electrons, they go on the central atom, even if it exceeds the octet. So we're going to put it right here. Now, rule of thumb, remember, we cannot put it, so if we have the bond over here, we can't add the electrons over here as well, because then that is a double bond. So when you put the extra lone pair in it, you want the extra regions. So remember we did the north-south, so your extra spaces to input things are going to be in between the regular north, south, east, west. And remember, we're going to max out at 6 regions. So here we have BH3, boron is 3 plus 3 times 1, which is 6. So we have BH, H, and H. So look, we have 6. We're done. And you're like, boron's not happy. Yeah, it's okay with 6, so it is happy. Resist the urge, because here's an aside. If you would do the same thing, but we're going to use fluorine, and I'm not going to fill up all the electron orbitals, but they would be filled. People are like, well, wait, we can do this and give that 8. Yes, you can, but you don't want to. It's happy without 8. It's happy with 6. Leave it alone. There are times when it'll pick up 2 more, but not in that structure right there. Okay, my last exception is the goofy nitrogen. So we have 5 plus 6 times 2, which is 12, 17. Okay, that tells you something right there. We have 17 electrons. That's an odd number. Nitrogen is going to be your central. So we have 2, 4, 6, 8, 10, 12, 14, 16, and we have 1 left over, so it goes on the central atom. Now, oxygen 1 has 8, oxygen 2 has 8, but nitrogen only has 5. It will take less, 1 less, but not that more. So one of these 2 is going to donate. So you're going to get nitrogen with a single bond to one oxygen and a double bond to the other one. Does it matter which oxygen you pull it from? No. More about that one later too. But if you noticed, we have a single electron. Well, this is actually a particular class of compounds. A single electron is a radical. Now, we're used to using the word radical. We talk about politicians and protesters of different varieties, etc. But in chemistry, a radical is anything that has a single electron. Now, the one thing that usually does hold firm is a radical is highly reactive. And it's hard to figure out where it's going to go. Because what's going to happen is the next thing it bumps into, and unless you can control what it bumps into, which you can't, it's going to take an electron from it because it's that reactive. So radicals in chemistry are highly reactive and very much likely to react as quickly as it can with any variety of things. The first thing it impacts. So the last thing we're going to do is look at oxidation numbers, formal charges, and actual partial charges in a closer look. We've done oxidation numbers from just the rules and the electron configurations. Now you're going to look at them with molecular applications. And formal charges, we haven't done that yet, we're going to. And actual partial charges, we talked about partial charges with polarity. So you can look at how it is with now respect to the actual bonds, if you look at it. All right, so we have started with the electron configurations. We have drawn them. At this point in time, I would pause and I would work some extra problems, either some of the extra problems I posted, some of the extra problems in the text. Starting next week, the lab will open where you'll do it, and online there's a molecule program that you can use, but you still need to start with the Lewis structures. So if it were me, I would work a few of these problems first, and then I go into the next section, because the next section is going to involve movement of the bonds throughout to give you different structures. There's a specialty to that. It's called resonance, and we'll get to that in the next segment.